As you can remember, on our previous lesson, we learned some facts about magnetic field. Today, we are going to start learning electromagnetic induction. Electromagnetic induction. Electromagnetic induction was discovered by Maxwell-Faraday in 1831. What is electromagnetic induction? As you can remember, magnetic flux is surface integral. Magnetic flux is surface integral of magnetic induction. This is magnetic flux, F magnetic flux, surface integral B ds. And what is electromagnetic induction? When magnetic flux changes in some way, magnetic flux through closed loop or closed circuit, when magnetic flux in closed circuit changes, electric current occurs in this circuit. So, for example, if we have electric circuit like this, and we have some internal magnetic field. So circuit in magnetic field with induction B. And let's imagine that the modulus of magnetic induction is decreasing. So it is getting lower and lower, and in this case, magnetic flux in this circuit will also decrease. It means that there will be electromagnetic induction. And how to define the direction of electric current. We can do this using Lenz rule. I'll type this rule because it is difficult. Maybe it is difficult to understand without typing. So Lenz rule. What is this? Lenz rule. Lenz rule. According to this rule, the current in the current induced in a circuit due to a change in magnetic field to a change due to a change in magnetic field. In magnetic field. Due to a change in magnetic field. Due to a change in magnetic field is directed to oppose the change. The change is directed to oppose the change in flux. And to exert a mechanical force which opposes the motion. Which opposes the motion. This is Lenz rule. Let's frame this in red. And let's try to define the direction of induced electric current. The change in magnetic flux is caused by decreasing of magnetic field. So the direction of, according to the Lenz rule, the direction of electric current will be that compensates this decreasing. The direction will oppose decreasing in magnetic field. So it means that according to the right hand rule, the direction of electric current will be this. Because according to the right hand rule, this direction of electric current leads to this direction of magnetic field, and this direction of electric current will oppose decreasing in magnetic field. Okay, do you have any questions about this? No questions. Okay. So let's continue learning electromagnetic induction. How to describe electromagnetic induction mathematically. To do this, let's have a look at conductive frame in internal magnetic field. Conductive frame. It looks like this. Conductive frame, conductive frame in magnetic field, in magnetic field, B, in magnetic field, and there is a little conductive stick that may slice on conductive frame. So frame and this stick are closed circuit. They are parts of closed circuit, and this stick moves to the right with velocity v. And because of this motion, square of this circuit changes, and this change in square leads to change in magnetic flux. So it means that electric current according to the Lenz rule should be directed to oppose changing in electric flux. Electric flux increases. So magnetic field caused by induced current should be opposed to the internal magnetic field, and because of this we can define the direction of induced current in this way. This is induced current. Okay, and how to describe this mathematically? According to this picture, motion of this vertical stick leads to change in area. I'll try to draw this on the picture. With I try to draw this in this way. So this is change in area of circuit, area of closed circuit. So the change in area ds is equal to if this distance is equal to L, and this is equal to dx, it means this that ds is equal to L dx. L dx. And according to the direction of induced current, according to the direction of induced current, we can define the direction of vector ds by right-hand rule. By right-hand rule. According to this rule, if all fingers without thumb shows the direction of induced current, thumb shows the direction of ds. So ds is here. ds is here according to the direction of induced current. So ds is from the screen to us. So it means that vectors b and ds are on the same line, but the directions are different. The directions are different. They are anti-parallel. Anti-parallel. And it means that product dot product b ds maybe I'll show change of magnetic flux. Change of magnetic flux. Change of magnetic flux. This is product b and ds, and this is b multiplied by ds multiplied by cosine 180 grades. 180 grades. 180 grades because the directions of vector b and ds are different, and these vectors are on the same line. And because of this, we have minus b ds. B minus b ds. And this is equal to minus b L dx. And it allows to find change in magnetic flux. The change in magnetic flux is derivative df by dt, and this is equal to minus d by dt minus b L dx this is equal to this is equal to minus B L dx by dt. And if we remember our first lesson, first lesson of kinematics, we can remember that derivative dx by dt is velocity, modulus of velocity. So this is minus b L v. This is minus b L and v. Minus b L and v. Minus b L and v. And okay, and what about this? Let's remember that conductor, every conductor contains free electric charges. Free electric charges inside it, and this vertical stick also contains free charges that move with it. And it means that there is a Lorentz force that acts on charges inside this moving stick. Lorentz force. As you can remember from our previous lesson, Lorentz force is equal to electric charge multiplied by electric field intensity, and this is equal to electric charge multiplied by vector product V and B. V and B. I think I can erase Lenz rule because we don't need it anymore. And in our case there is no electric field. So this is equal to 0, because in our case there is no electric field, only magnetic field. So we have that Lorentz force caused by motion of vertical stick on the frame. It means that this is equal to Q V multiplied by B. Multiplied by B. Multiplied by B. Let's find modulus. Let's find modulus of Lorentz force. Let's find modulus of Lorentz force. This modulus is equal to F L is equal to modulus of FL, and this is equal to, let's suppose that charge is positive, so it can be written outside the modulus, vector product V and B, and according to the properties of vector product, it can be written as Q V B multiplied by sinus and angle between vectors V and B. Vector V is on the screen, and vector B is perpendicular to the screen. It means that angle between vectors V and B is equal to 90 degrees. 90 degrees. It means that this angle is equal to 90 degrees. And sinus of 90 degrees is equal to 1. So this is equal to Q, V, and B. Q, V, and B. Okay, do you have any questions about this? Do you have any questions? No questions. Okay, so let's find the direction of Lorentz force according to the left hand rule. According to the left hand rule. It is necessary to put left hand rule like this. Like this. Left hand rule. And vector B should be directed to the palm of left hand. Vector B is to the palm of left hand, and vector V, vector of velocity, is here. And in this case, some will show the direction of Lorentz force. The direction of Lorentz force. The direction of Lorentz force. This is the direction of Lorentz force, FL. The direction of Lorentz force. So, and if we have a look at our picture, we will see that Lorentz force is directed like this. According to the left hand rule. Lorentz force is directed from down to up on the screen. And this is the direction. And this direction allows us to find work of this Lorentz force. Work of this Lorentz force caused by motion of this horizontal stick. So let's find this work. As you can remember from mechanics, this work is equal to integral from 0 to L, linear integral from 0 to L, F L d R dr. But according to the direction of electric current, electric charge moves from down to up. From down to up. It means that the directions of Lorentz force FL and vector dr, these directions are the same. So the direction of FL and dr are the same. Directions are the same, and it means that scalar product or dot product FL dr vector is equal to F L dr cosine of 0 degrees. 0 because the directions of vector F and dr are the same. And cosine of 0 is equal to 1. So this is equal to FL dr. FL dr. And we can use this here. So we can rewrite this integral without vectors. So this is equal to FL dr. And this is equal to Q V B integral from 0 to L dr. All value that don't depend on dr may be all values that don't depend on dr may be written outside the integral. So it means that it can be written Q V B UVB integral from 0 to L dr. And this integral is simple to calculate. It is equal to Q na B Q multiplied by B L V. Q multiplied by B L and V. BLV. And from this we have that BLV is equal to work divided by charge. But as you can remember from one of our previous lessons, work divided by electric charge is equal to electromotive force. This is equal to electromotive force, where lower index I stands for induction. So this is electromotive force of induction. and because of this we have lower index I. Okay, do you have any questions about this? No questions. No questions. So I'll clean I'll clean the screen. I'll clean the screen. I'll clean the screen. I'll clean the screen. Not all the screen, but some things on this screen. I'll clean some things on the screen. So here we have okay. So we have obtained change of magnetic flux, and we have obtained electromotive force of induction. And for this system, this is the same, BLV, but with different signs, plus and minus. And from this, we can get Faraday's law of induction. Faraday's law of induction. Faraday's law of induction. Faraday's law of induction. According to this law, electromotive force of induction is equal to minus derivative of magnetic flux by time. Is Faraday's law of induction, and this law is right not only for this ray. This law is right for any case, for any system, and this law allows to generate electric energy. For example, in a water power plant or a wind power plant, there are circuits. There are circuits that have form of conductive frames, and these frames rotate in magnetic field, and because of this rotation there is a change in magnetic flux, and this change in magnetic flux generates electric energy. So the theoretical base of water power plant or wind power plant is Faraday's law of induction. Okay, do you have any questions about this? Do you have any questions? Okay, it is necessary to say that this is magnetic flux. Magnetic flux. Magnetic flux. Magnetic flux. And it is necessary to say that there are special units. There are special units for magnetic flux. There are special units for magnetic flux. These units are Webers. Webers. Weber is a unit for magnetic flux. Weber is unit for magnetic flux, and short form is WB. Is WB. So and 1 Weber, 1 Weber is equal to 1 Tesla multiplied by 1 square meter. Multiplied by 1 square meter. This is Weber. And it is necessary to say that in many practical cases, it is necessary to increase magnetic flux. To increase magnetic flux in order to increase electromotive force of induction. How can we increase magnetic flux? The first way is to increase magnetic induction. As you can remember, magnetic induction depends on magnetic permeability, depends on relative permeability mu. And this mu depends on material. So we can fill circuit with material that has high value of relative permeability mu, and in this way we can increase magnetic field and increase magnetic flux. And the next way is to connect electric circuits, is to connect closed circuits in series, and in this case we will have inductant or solenoid. Inductor or solenoid, or induction coil. What is this? This is conductor that has form similar to the spring, that has n turns, spring with n turns, and each turn of the spring is a little circuit, is a little loop, and in this case all turns connected all turns connected in series, and as you can remember, for connection in series, electromotive forces add to each other. So we can write generalized Faraday's law of induction. We can write this in another way. So according to this Faraday's law, I'll write this Faraday's law of induction. Faraday's law of induction for n turns. In this case, we have that electromotive force is equal to minus d psi by dt. This is Greek letter psi. And psi is equal to, where psi is equal to number of turns multiplied by magnetic flux, and this is flux linkage. Is flux linkage. Psi is flux linkage. This is generalized form of Faraday's law of induction. Okay, and it is necessary to draw red frame. So for n turns, we have Faraday's law of induction in this form. Okay, do you have any questions? Do you have any questions about this? No questions. Okay, let's say a few words about solenoid or inductor or induction coil. I'll write a formula for magnetic field inside it. We will prove this formula tomorrow. Morning, but today we need this formula, so I have to write this without proving. So solenoid or inductor or induction coil. Induction coil or induction coil. What's wrong with this? Solenoid or inductor or induction coil or induction coil. Oh, this is correct. Or induction coil. This is this conductor that has form of the spring. It has form of the spring. Let's consider that it has n turns, and it has length. It has length that is equal to L. That is equal to L. Length of inductor. Length of inductor with n turns. And what about magnetic field inside? What about magnetic field inside this induction coil? Number of turns per unit of length is equal to this, and magnetic field inside this inductor is equal to mu 0 n electric current, and this is equal to mu 0 n divided by L, and divided by L multiplied by electric current. Tomorrow we will prove this formula. But today we need this, so, and because of this I have written this formula. Solenoid is a very important part of the most of electronic devices. For example, in your laptops, computers, iPhones, there are a lot of inductors. Is very important element, and because of this it is necessary to know properties. It is necessary to know properties of this element. Okay, and let's write another form. Let's write another form of Faraday's law of induction. Let's remember that electromotive force. Let's remember from our previous lessons that electromotive force can be written as integral of electric field, by dl. Electric, but not electrostatic, because in the case of electrostatic field, this integral is equal to zero. But here we have electric but not electrostatic field. The difference is that electrostatic field is part of electric field that produced by fixed electric charge. Fixed means that they don't move. Electromotive force can be written in this way, and we have magnetic flux here. So derivative of magnetic flux can be written according to this. I have written partial derivative because magnetic field may depend not only on time but also on coordinates x, y, z. So according to this, we have that this is equal to surface integral SL d by dt by dt by dt ds. Okay, and so let's substitute this formula here and here, and from this we have obtained so-called Maxwell-Faraday equation. Maxwell-Faraday equation. Maxwell-Faraday equation is another form of Faraday's law of induction. Maxwell-Faraday equation. Maxwell-Faraday equation. According to this, linear integral of E dl is equal to surface integral first derivative of magnetic induction by time and integration by ds. Maxwell-Faraday equation means that change in magnetic field produces electric field. So change in magnetic field produces electric field. Produces electric field. And this fact uses, for example, in induction ovens. Maybe you are familiar with this. Induction oven is very effective oven it saves a lot of energy, and it is very useful. It is very useful. Sometimes it is very useful. Okay. Okay. Do you have any more questions about this? No questions. No questions. Okay. If there is no questions, I will clean some formula that we don't need anymore. So I will clean this. I will clean this. I will clean this. I will clean this, but we still need this, and we still need this. We still need this. We still need this. We still need this. Okay. If we have conductor, with electric current, we know from our previous lesson that this electric current will produce magnetic field, and this magnetic field will produce magnetic flux through this circuit. So electric current in circuit produces magnetic field. According to Biot-Savart law. Is equal to mu 0 divided by 4p electric current vector product dl multiplied by r divided by r to the power of 3. Okay, and it means that magnetic induction is proportional to electric current. But magnetic flux is defined by this surface integral b ds magnetic flux, and it means that magnetic flux is also proportional to electric current. So we have b proportional to electric current, and from here we have that f proportional to electric current, and it means that flux linkage is proportional to electric current. proportional to electric current. Proportional to electric current. And what does it mean? It means that we can write that psi is equal to L multiplied by electric current, where L is inductance. L is inductance. Where L is inductance. In this case, when electric current produces electric current in circuit produces magnetic flux through the circuit. So electric current in circuit produces magnetic flux. In this circuit, this case is called self-induction. So in case of self-induction, we have that that flux linkage is equal to L multiplied by E. So in case of self-induction, psi is equal to L multiplied by E, where L is inductance. L is inductance. Where L is inductance. Where L is inductance. Okay, do you have any questions about this? Do you have any questions about this? No questions. No questions. Okay. If there is no questions, let's find inductance of solenoid. Let's find inductance of solenoid. According to this formula, we have that we have magnetic field. And it is necessary to say a few words about magnetic field inside solenoid. Magnetic field inside solenoid. It is known that magnetic field inside solenoid is homogeneous. Magnetic field inside solenoid is always homogeneous. So I can draw this like in this way. Magnetic field inside solenoid is homogeneous. This is B, and the square area of one turn of inductor, is ds or s. This is area is s and has the same direction, has the same direction as vector B, vector of magnetic induction. And it means that in this case, magnetic flux is equal to integral SL B ds and this is equal to, as you can see from our picture, vector B is the same in each point inside inductor, so it doesn't depend on ds, so we can write this is equal to SL ds, and this is equal to B S and this is equal, as you can see, B has the same direction as S. So this will be B as cosine 0 degrees. This is equal to BS. This is equal to BS. And this is equal to, let's remember that we have formula of magnetic field of inside solenoid. It is necessary to hide vector. It is necessary to remove vector above B, because this is modulus of vector B. So we have mu 0 n divided by L S electric current E. Okay, and what about flux linkage? Psi is equal to number of turns multiplied by magnetic flux, and this is equal to mu 0 n squared divided by L S I, and this is the same as mu 0 n to the power of 2 divided by L to the power of 2 multiplied by SL multiplied by electric current, and this is the same as, let's remember that number of turns divided by the length of solenoid is equal to concentration of turns per how to draw this line, I'll draw this here. Yeah, so this is mu 0 n to the power of 2 v electric current I. Okay, do you have any questions about this? Do you have any questions? No questions. No questions. Okay, if there is no questions, I will clean some formula from my screen. I'll remove some formula from the screen. I'll remove some formula from the screen and I will leave only some things that I need. So we have obtained that inside solenoid we have flux linkage. That can be found by this formula. And according to this, we have that this is equal to L and this is equal to L, inductance of solenoid. So we have obtained that L is equal to mu 0 n to the power of 2 divided by the length of solenoid multiplied by square of turn, and this is equal to mu relative permeability of free space multiplied by concentration of turns and multiplied by volume inside solenoid. Okay, do you have any questions about this? No questions. Okay, so I will clean this, and I think it is necessary. To add this formula. Here. It is necessary to add this formula here. So we have this for solenoid. Okay, and the last thing is in case of self-induction, in case of self-induction, we can make substitution. We can substitute this here, and we will obtain that electromotive force of induction. I will make lower index s. That means self-induction. Self-induction is equal to minus L di divided by dt. Di by dt. This is in case of self-induction. In case of self-induction, and I'll add this here. I will add this here. I'll add this here. I'll add this here. Okay, do you have any questions? Okay. What does it mean? What does it mean? It means that if we have electric circuit with electric current I, and if this electric current changes, the electromotive force of self-induction will oppose change in electric current. And first of all, it will oppose fast change of electric current. It will oppose fast change in electric current. And because of this, some elements with high inductance may be used to suppress high frequently noises in electric circuits. I'll show a picture here. I'll show a picture from the internet. Picture from the internet. Picture from internet. This is here. This is here. As you can see on the right side of the screen, there is a black cylinder on a wire. This black cylinder is ferrite bead. What is this? Ferrite bead is element that has high inductance, and because of Faraday's law for electromagnetic induction, it will suppress high frequency noises. It will suppress high frequency noise. It is written here, you can see. And okay, do you have any questions about this? Do you have any questions? No questions. Okay, if you don't have any more questions, thank you for your attention. Thank you for your attention. I hope to see you tomorrow. We will do some exercises. We will do some exercises, and I hope we will understand. We will understand this difficult material better.
Okay, teacher. See you tomorrow. Have a nice day.
Have a nice day.
Thanks, teacher. Goodbye, teacher.